Harmonic Gestalt. Gestalt theory has always posed a profound challenge for neuroscience with its peculiar properties, emergence, reification, multistability, and invariance, in which the principle appears to be that the interaction between innumerable local forces simultaneously and in parallel produce a global gestalt, reifying the most regular interpretation and thereby suppressing its alternatives, or becoming multistable between them. Harmonic resonance exhibits exactly those properties. So, a harmonic Gestalt theory, to combine harmonic resonance with Gestalt theory, Gestalt theory suggests that the visual system reifies every possible alternative in parallel as it picks the simplest alternative by the principle of Prägnanz, or Gestalt goodness, Gestalt simplicity. Detection and completion are one and the same process. It is the symmetry of the simplest perceptual interpretation that allows it to amplify itself by resonance. The very concept of this computational solution seems completely implausible in the absence of a harmonic resonance principle. So Gestalt involves a simplicity metric, or Prägnanz. So, for example, for this particular stimulus over here, perception seems to prefer this interpretation because it's simpler than the alternative. There's a hierarchy of Prägnanz. For example, equilateral triangle is more regular than an isosceles triangle, which is more regular than an irregular triangle. And likewise with the square, that's more regular than a rhombus, more regular than a parallelogram, a trapezoid, or an irregular quadrilateral. So Prägnanz is a function of the information content of the shape. The shapes that have more articulations require more information to record their parameters. The tendency towards Prägnanz in perception is the perceptual equivalent of Occam's razor. The simplest interpretation is most likely to be right. So what appears to be happening in perception is a kind of inverse projection where the two-dimensional retinal input is projected in depth into a spatial representation, and from whence interactions between the different interpretations lead to the emergence of the most probable one, and at that point the other alternatives fade. In 1960, Hochberg and Brooks devised a quantitative metric for Prägnanz. They presented a bunch of ambiguous stimuli like these to subjects and asked them to rate which are more likely to be perceived as 3D shapes and which are more likely as 2D shapes. And then from these experimental results, they devised this quantitative metric that you count the number of sides of the same length in each of these figures, and the number of angles of the same size, and we compare this metric for 2D versus 3D interpretation, and it will explain these experimental results. So, for example, for this figure here, which tends to be seen as 3D, but it can be seen as 2D with the help of some colored lines, and if we count the number of sides, there are 16 different sides and 5 different sides lengths for this 2D interpretation. On the other hand, as a 3D figure, it has 12 sides and 1 side length, and all the angles are equal. So this metric accounts for the perception of Prägnanz. This is an interesting problem because it exemplifies the computational issues inherent in the problem. First of all, it requires human observers to see the 3D percept in the first place. Can we automate the process of spatial perception? This is a profound challenge that requires an unconventional approach. I propose a harmonic gestalt, sound from structure, based on the principle that a line will vibrate at a frequency which is the reciprocal of its length. Frequency equals 1 over length. So, for example, in this percept, this vertical line over here would be represented by a musical tone, that is a function of its length. If we now take a look at the two-dimensional percept and we employ a different tone for each line length, then you will get a sound like this. Here, on the other hand, is a three-dimensional percept, and this has a single tone. It is thus judged to be the most pregnant. So the frequency of a line is 1 over its length, and this representation is by its very nature invariant to rotation, and it's invariant to translation. All of these lines would make exactly the same tone. The invariance is a property of sound and other wave-based systems. This simple property has extraordinary consequences when using sound to represent structure or structure to represent sound.
This is my Harmonic Gestalt program written in Python using Matplotlib, available from my GitHub site. It presents a stimulus screen. If you click on the screen, it produces a stimulus point. If I put on another point, we get a musical tone, and the frequency of that tone is a function of the separation between the 2 points. Down here we see a Fourier transform. There's the DC term at the center. The left and right sides are symmetrically identical to each other. So this is just one frequency. These 3 peaks here represent one dominant frequency that varies as a function of separation between the dots. Now, if I add another point, let's say over here, the distance between these 2 dots and those 2 dots is about the same. But now we've got a new frequency over here.
Very faint.
Due to the proximity of these 2 points, we can see that over here on the Fourier transform as the peak out here. And if we move this point slowly to the left, this distance increases as this one reduces and this one stays the same. And what you see, let the audio catch up, is a change in the harmonic content of the sound as a function of the configuration of the 3 points. When the 3 points get close to an isosceles configuration, you can hear an extra harmony in the tone due to the fact that it's now reduced to a simple 2 peaks. And if we now move this dot up and listen to the change of tone, as these 2 sides get longer, then these 2 peaks approach each other. And as we get to an equilateral configuration, these 2 peaks merge into one. You have to find the sweet spot where it's in perfect harmony. There we go. So there's the perfect harmony of the equilateral triangle. This harmony is independent of the orientation of the pattern. It's a totally intrinsic metric. And to some degree, it is also invariant to the scale of the pattern, because although when we scale the pattern smaller, the frequency goes up, but the, what happened there? But the basic waveform, the fact that it's a single peak for this equilateral configuration, remains unchanged through the scaling.
So we have a representation here that is translation invariant, it's rotation invariant, and to some extent it is also scale invariant. That is because it employs an intrinsic metric, as does Clifford algebra, in which everything is relative to everything else. It's a relative scale. Now, we talked about the hierarchy of pregnance and how pregnance is a function of the information content of the shape. In terms of a harmonic theory, we can say that pregnance is a function of the energy required to sustain that resonance. So the tendency towards pregnance can be seen as a loss of higher harmonics due to impedance, and therefore it tends to favor a lower resolution, lower harmonic representation if it fits.
If we click points randomly on the screen, we get an ugly, inharmonious sound. Here's a harmonious tone from 4 points in a line. Equilateral triangles pattern. In fact, any pattern that has symmetry or periodicity is guaranteed to register with high pregnance. If we have two stimulus points on the screen with the corresponding sound, these 2 points themselves suggest other points that are in harmonious agreement with them. For instance, this one here, observe the peak out here becoming a single peak when it's most harmonious. Or maybe we can move this one over this way. There we go, that sounds better. So every dot that you add changes the field around it.
Part 9, Feed Forward and Feedback Model.